In this PowerPoint, we're going to talk about vectors and two-dimensional motion. So the topics we're going to talk about are going to be vectors and their properties, components of a vector, two-dimension motion in two dimensions, and relative velocity. So a vector has a direction and a magnitude, but it doesn't necessarily have a specific place that it has to be. So we can actually move vectors around anywhere we want as long as we keep the direction and magnitude the same. And when I mean direction, I mean the way that it's pointed. We're going to basically measure the angle with respect to the horizontal, and that angle, as long as that angle stays the same, and as long as the length of the vector, which represents the magnitude, stays the same, then that vector can be moved anywhere. So when we have two vectors that have the same length and the same magnitude, then we say that those two vectors are equal. Now, where we run into trouble with this is if we have two velocities where, let's say you have one that's 5 meters per second north and the other's 5 meters per second east. Now, even though they both are 5 meters per second, because their directions are different, then that means they are not the same vector. So this one would be a 5 meter per second to the northeast. This one's 5 meters per second to the northeast. Those would be the same vectors because they have the same magnitude and the same direction. Scaling vectors, so essentially what you do is when you multiply a vector by 2, you simply change the magnitude, so the length of the vector doubles, but the direction does not change. So scaling vectors, you only change the magnitude, you do not change the direction. Scaling a displacement vector, so when you take that displacement, you divide by time. Basically what you do is you now turn it into a velocity vector. So displacement, the direction of the displacement will be the same as the direction as the velocity, because when you divide by a scalar or multiply by a scalar, that does not change the direction, but it does change the length of the vector. Same thing with a change in velocity divided by time, that gives us acceleration. So similarly, we divide by a scalar, so it changes the scaling, but it doesn't change the direction of the vector. All right, so graphical analysis or graphical addition of vectors. So when we have two vectors, we can add them together. To graphically add them together, essentially what we do is we call the head-to-toe method. And what we do is we have our first vector of A, our second vector of B. We take the tail or the toe of B and put it at the head of A. As long as we don't change the direction, we simply move it over. And then the resultant, or when we add these vectors together, the one vector that these make start at the beginning of the first one and end at the end of the last one. So that is going to be my resultant vector, and I could take these two vectors and I basically put them together to get one vector here, and we call that vector C. So vector C is going to be A plus B. Now I will tell you that it doesn't matter if you put B at the tip of A and then go from the beginning of A to the end of B, or if you want to, you could put the tip of A at the beginning, or I'm sorry, the beginning of A at the tip of B, and then you would have from the beginning of B to A, it would be the same magnitude and same direction. So this property is actually commutative, meaning A plus B for vectors is the same as B plus A. Subtracting vectors. Now, subtracting vectors seems a little weird. It's like, well, how do I subtract one from the other? But really what it is subtraction of vectors is going to be addition. We literally just take a negative of one of the vectors. So when I have b minus a, really what I'm going to do is I'm going to take b plus a plus a negative b. So a minus b is really going to be a plus a negative b. That negative implies direction. So when I put a negative on there, I literally flip the direction. So instead of going down and to the right, it's going to go up and to the left. It's going to have the same angle, but it's going to go in the opposite direction. So then after I flip b, then I add the two vectors together like I did before, the head to toe method. So the toe of the b vector goes at the head of the a vector, and then the resultant starts at the beginning of a and ends at the end of b. Now, as long as you keep b negative, then I can put a at the end of b or negative b at the end of a and still get the same direction, same magnitude. So as long as we have this, as long as we put the negative with the b, then this is going to be commutative as well. Negative b plus a will be the same as a plus a negative b. So that gives us our vector c that is going to be a minus b. Now, components of a vector, essentially we have this vector that's off at an angle, but we have parts that are in the horizontal direction and a part that's in the vertical direction. So essentially we make a right triangle out of this. We have this vector A in the x direction, this vector A in the y direction, and you can see that it makes a right triangle. And those two components are always going to be perpendicular. Whenever you have components of a vector, they are always perpendicular to each other. So we move this component over to the y-axis. This is referred to as a projection. So that is projected onto the y-axis, but you can see that the length of the vector in the y direction matches this vector that has x and y together. So we break it into components where we make a right triangle out of it. Now the vector components, the magnitude is going to be the length of the vector, and then we project the x component of it is going to be equal to a cosine of theta. Now keep in mind that this side, the x side, is adjacent to that angle, and a is the hypotenuse of that triangle. So if we take the adjacent and divide it by the hypotenuse, that equals cosine of theta. So then when we multiply by the hypotenuse, that's where we get our component in the x direction. Likewise, the component in the y direction is going to be opposite this angle. Now when we deal with vectors, the angle that we use, it may be this angle here or maybe this angle over here. So the sine and cosine may change. One of the ways that we always measure direction sometimes is that we have the x direction, and we always measure the angle from the x. That's one method of doing it, is where you start from the x-axis and you measure all the way around, wherever your vector is, you measure all the way around that full angle. So if it's 120 degrees or 250 degrees, wherever it is, you always measure from the x-axis. If that's the case, then the y component is always going to be sine and the x component is always going to be cosine. But if we change it, sometimes we measure a vector simply if something's off to the northwest, then we basically measure the angle from the north axis, and in that case we would have to determine which one's going to be sine and which one's going to be cosine. So these components, you can see that the magnitude of A, since we're dealing with a right triangle, the magnitude of A squared will be equal to the magnitude of A x squared plus ay squared, and that would give us our magnitude for A. So if we have the components themselves, then we could figure out what the magnitude of the vector is by using Pythagorean theorem. Now the angle, we have the opposite side. If we know the y component and we know the x component, then we can use that opposite and adjacent, which is going to be tangent of theta, and that's going to be equal opposite over adjacent. So it's ay over ax. So to find that theta, we take the inverse tangent of opposite over adjacent. All right, so now we have our two vectors, and we added them together graphically, meaning that we start from the beginning of the first one and end at the end of the last one. Now I want to add them together mathematically. So what we do, the way we do that, is we have to break down each vector into its components. So A has a component in the x direction, but B also has a component in the x direction, and the resultant is actually going to be both of those x components added together. For the y direction, we do the exact same thing. So let's break down A and B into X components and Y components. All right, so you see if you use A in the X direction, that's this component right here, and then A in the Y direction, that matches that right there. And then B in the X direction would be this far, and then B in the Y direction would start, since B starts here, it would go up from there. So you see that R, the resultant, is going to be A and B in the Y direction added together, gives me the Y component of R total. And then in the R in the X direction is going to be A of X plus B of X. So each component in the X direction or Y direction will add together to give the resultant in that direction. So once we break these down into X and Y components, we can add those components together and then make a big right triangle out of those components in order to figure out the magnitude and the direction of the resultant vector. Now we can see with this this slide we have AX is A cosine of alpha, so this angle right here, BX is B cosine of beta. So keep in mind that you have to keep the angle for the respective vectors. So don't use alpha for the for vector B, because that's not the angle. So the X component and the Y component for each one of those, and then they add together for in the X direction, they add together in the Y direction, and that gives me the total in the X and the Y. And then we use a Pythagorean theorem to figure out the resultant of the vector. Okay, so now we're going to take this object and we're going to add multiple vectors to it. We got force 1, force 2, force 3, and force 4. Now, addition of vectors is completely different than addition of scalars. Scalars is what you're used to in your math class when you take 2 plus 3 and you get 5. When it comes to vectors, adding 2 and 3 gets complicated because that 2 and that 3 have a direction. For example, if you have 2 to the left but then 3 to the right, then that would be a -2 and a +3, which would be equal to 1. So it's actually possible to add a 2 and a 3 with vectors and get a 1, or something in between 1 and 5 if it's at an angle. All right, so the first thing we have to do is we have to take each one of these vectors, we have to split them in X and Y components. So we're going to add all the vectors together. All right, so vector addition is not taking the numbers and adding them together. You got to figure out the components in the X direction and the components in the Y direction and add each component together. So we have these, each force, 50 newtons at 30 degrees, 100 newtons at 135 degrees, 30 newtons at 250 degrees, and then 40 newtons at 300 degrees. So all of these angles are measured from the positive x-axis. So at positive x-axis, you go around counterclockwise until you get to the vector itself. That's going to be the angle used. Now, if we always use the x component to be cosine, the y component to be sine, as long as we're measuring from the x-axis and going clockwise or counterclockwise, then we can literally plug these numbers into these equations and then figure out their components. And what's good about this, as long as you're in degree mode, your calculator will actually get you the negative when you do this. So 100 cosine of 135 degrees gives you -70.7, and then 100 sine of 135 degrees gives you positive. All right, and then the third vector, both of the x and y components are in the third quadrant, so they're both negative. And then the last one, the x components in the positive direction, then y components in the negative direction. Now we can add all of these together. So as long as the vectors are all in the same dimension, meaning all in the x direction, all in the y direction, we can add them all together. Now, once you get them all in the x direction, all in the y direction, now we make our new vector, and we can use Pythagorean theorem to figure out the hypotenuse, the magnitude. So keep in mind that you're going to square a negative here. So sometimes whenever I do this, I ignore the negative until I talk about the direction later, because you need to make sure you square that negative. If you plug that -17.7 squared into your calculator will square the 17.7, but not the negative. So sometimes it's easier to just drop the negative and then deal with the negative later. So we get the resultant force is going to be 37.4 newtons. Now to find the angle, we have to use inverse tangent, because we have the opposite and we have the adjacent. So the opposite side here is 32.9. And then the adjacent side here is 17 or -17.7. Now, when you plug that in, you get an angle of -61.7 degrees. Now that describes this angle, but if you remember, all the vectors were measured from the positive x-axis. So to get the angle from the positive x-axis, we need to add this -61.7 to 180 degrees, and that gives us our angle for this resultant vector is actually going to be 118 degrees. So our resultant vector is going to be 37.4 newtons at 118 degrees. All right, so what about these next vectors? So we got these several vectors. There's four more vectors for this example. 90 newtons at 45 degrees, 80 newtons at 150 degrees, 50 newtons at 220 degrees, and then 70 newtons at 340 degrees. So go ahead and try this. And if you break it into x and y components, you get a total in the x of 63.6, negative 69.3, negative 38.3, and then 65.8. That adds up to a total in 21.8 in the x direction. And then 63.6, 40, negative 32.1, negative 23.9. That gives us 47.6 in the y direction. So then we use Pythagorean theorem to figure out the hypotenuse. That's going to be 52.4 degrees. And then to find the angle, both of these are positive. So positive x, positive y, that means we're going to be in the first quadrant. So the angle with respect to the x-axis, opposite over adjacent. So 47.6 divided by 21.8. We take inverse tangent of that, and we get an angle that is going to be equal to 65.4 degrees.